All right, sorry about the technical difficulties. So for our seminar this semester, we have two speakers who are either current or recent graduate students or postdocs who have worked on INRC funded research projects. Now, before we begin, I just have a few housekeeping items. First, this is a hybrid meeting. For those of you online, you can type your questions into the chat box. Ask them at the end of the presentations. For those of you who are in the room in Ealing's Hall, we will have a time at the end of the talk where you can ask your question directly. And then second, this webinar will be recorded and posted to the INRC's website along with previous seminars. So for our first speaker today, we have Zhushan Du. She is a PhD student in the Department of Economics at Iowa State University. She is working on research with Dr. Hongli Feng and Dr. Jay Arbuckle. And she's going to be presenting on Adoption Isn't Forever, analyzing temporal variability in cover crop adoption with farm level data.
Good afternoon, everybody. It's a great honor to present my joint work with Dr. Hongli Feng and Dr. Arbuckle on the topic Adoption is Forever. And I would like to thank our Nutrient Reduction Center for supporting this project. And for this study, we look at the adoption dynamics of conservation practice, cover crop especially, with farm level data. Okay, thanks. So we all know that conservation practice can bring multi-dimensional environmental benefits. For example, reduce soil erosion, reduce nitrogen leaching to freshwater system, and also contribute to soil organic carbon accumulation in the land. According to the literature, cover crop can substantially reduce nitrate leaching by, on average, 50%, with a range of 5 to 21 pounds per acre per year, and it can also contribute to around 0.4 to 0.4 metric ton of carbon per acre per year. However, despite the lots of research focus and the substantial financial incentives into the conservation practice, the adoption rate is still far way beyond what's considered to be win-win strategy for both farm productivity and also environmental benefits. For example, in order to achieve our 45% nutrient reduction goal, cover crop has to be planted for 10 to 14 million acres. However, the current planted cover crop is only 1.3 million acres, which is just 10% of what's ideal. Another important thing is that for many conservation practice like cover crop and no-tillage, in order to achieve long-term environmental benefits, farmers have to adopt the conservation practice in the long term. For example, suppose a farmer do the no-till for the past several years, and there's just 1 year he switched to the tillage, the soil sequester in the carbon will be released to the atmosphere, which will lead to a significant loss of adoption benefits. However, the existing literature from both the perspective of sociology and economics, researchers has focused largely on the initial adoption with the implicit assumption that once farmers try the conservation practice or the technology, he will just continue to use it. However, it may not be the case, because at the beginning of the adoption of a new technology, it's more like a trial. When farmers learn more about the technology or conservation practice, he may start to realize it's not good for their farm. So he may just stop using it or alternating the practice. It's not just the hypothesis, but also documented in the literature. For example, Don Ito look at the discontinue behavior among cover crop early users, and he identified 17% of disadoption rate. For no tillage, Wheat and Clausen found that use ARMS data found 30% of farmers switch from no-till to other tillage practice. And also using aggregate data, Plastina found that across whole US counties, 50% of counties has experienced disadoption, which is a substantial magnitude of disadoption. So for this study, we try to answer two questions. The first is that how does adoption status change over time, and we use Sankey chart to check the adoption status transition between years, and we group farmers based on their adoption transition behavior. And the second question we want to answer is that what factors are driving the adoption and disadoption behavior, and we use econometric methods and machine learning methods to predict adoption and disadoption. And we use data from Iowa Farm and the Rural Life Poll, and we use 3 waves of the survey, which has the information of past year cover crop usage. And for the 3 years, that's 2014, 2016, and 2018, the response rate is around 50%. So here is the Sankey diagram, which is very powerful. For each group, for the vertical bar, it represents each study year, that is 2013, 2015, and 2017. Because in the survey, we ask farmers whether you adopt cover crop in the past year. And based on the adoption status on each year, either adoption or non-adoption, we have 8 streams of flows of adoption profile. For example, a farmer can be adopter, 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 or he can be adopter, non-adopter, 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 or he can switching his behavior in this 3 study period. So what's fascinating about this about the Sankey diagram is that it cannot help us to track adoption transition across period. The width of each stream represents the percentage of the group of farmer out of the whole sample. And the first thing we can see from the graph is that we see a gradual increase of net adopters, starting from 7.7% to 20.9% in 2017. However, when we look further into the adopters, we only see 6.6 farmers report continuous usage like in 3 years. In contrast, we only observe we can observe 64.5 who reported a non-usage in all of 3 years, and we called these 2 groups continuous adopters and continuous non-adopters. What's most interesting here is the intermittent adopters. That represents farmers reported at least 1 year use during these 3 years. And as we can see from the figure, the intermittent adopters is almost 30%, which is almost 5 times as continuous adopters. And the second thing we can see from the Sankey chart is although we only see a net increase of 2.1 from 2013 to 2015, it is actually a new take up of 10.6 adopters, but significantly offset by 8.5 disadoption, which leads to a net increase of 2.1. That is, in other words, the disadoption rate is actually 4 times high as the net adoption rate. And a similar pattern can be observed from 2015 to 2017. We further translate the individual transition behavior to the aggregate trend. We started with the baseline adoption in 2013, which is 92 farmers marked as the light green area. And we use the darker green area to represent net increase. And we want to highlight is that for the yellow area, we marked as the cumulative adoption, which represents farmers at least tried once in the 3 years. And it also represents a hypothetical scenario is that if this adoption would never occur, or intermittent use never occurred, once people try it, we continue to use it, the cumulative adoption is actually twice as the initial adopters. So the second question we want to answer is that what's the driving factors behind adoption and non-adoption? So we use traditional econometric method, which is logistic regression, and also machine learning method to do the prediction. So what we did is that we used the past 2 years variable and information, and we try to predict adoption and disadoption in the third year. From the model, all our result shows that random forest, which is the common used machine learning method, can achieve 7% higher accuracy than logistic regression, and it's more robust to the outliers. Looking at the marginal effects from the logistic regression, we see that past adoption behavior is a strong predictor to the third year adoption. And also we see a complementary use of no-till. For example, if a farmer used a no-till in the previous years, he's more likely to do the cover crop in the next year. And the complementary use of multiple practice is also documented in the literature. And we also found the farmers' concern in terms of lack of knowledge of cover crop is a huge barrier of adoption. The marginal effects from random forest model give us more detailed understanding of each variables. Additional insight can be seen from the accumulative local effect plot is that cost share has a positive correlation with future adoption, and the precipitation shows a U-shape which aligns with the previous literature because cover crop can adapt to both extremes of precipitation level. And the crop insurance is also a strong predictor for future adoption. So in summary, we categorize farmers into 3 groups: continuous adopters, continuous non-adopters, and intermittent adopters. It gave us a more refined understanding of not just a snapshot of one-time usage, but also check the transition and the trends over time. And we also want to highlight the cumulative adoption compared to the net adoption. Our data shows that the cumulative adoption can be twice the amount of net adoption if this adoption could never happen. And we also advocate a paradigm shift from both research and the policy focus largely on the initial adoption to a more integrated analysis on both initial adoption and post-initial adoption behavior. We did a little bit back of envelope analysis of the disadoption. In our sample alone, we see 15% of disadoption. It can actually lead to 1 million to 4 million pounds of nitrate reduction more per year. And it can also help to sequester 8,000 to 80,000 of soil carbon. What's the other insights from the prediction accuracy? Suppose if we can have farmers past information and his characteristic data, we can better help the extension staff to predict who is more likely to disadopt. It actually helps the extension and conservation agency to better allocate the funds. For example, provide more targeted cost share funding and also technical assistance for those who are more likely to disadopt. We also did back of envelope estimate of the prediction accuracy. The 7% improvement in accuracy just in our sample alone can help to better allocate $230,000 when scaled up to just in our 500 farmers. When scaled up to border population and considering the substantial county level disadoption rate, the improved accuracy, as I said, can help better targeting and better allocation of the cost share funding, therefore increase the cost effectiveness of those $1 million, reduce administrative burden, and more support and higher environmental benefits through continued adoption. So that's it. Thank you.
We have time for a couple questions before we move on to our next presenter.
So your last survey was in 2017.
Yes.
Do you have plans to do a one soon to kind of get an idea? Because just from my gut feeling from driving around, I guess I feel like since 2017 there might be more.
Yes, we are considering using more recent data to see whether the trend has changed.
Were the same questions asked in the Farm and Rural Life poll since then, so that you could look at some of that similar information?
Yeah, we have in 2021, 2023, I guess probably in 2025 as well. But the 2025 data has not been read.
Based on what you found, are there any additional questions you think helpful to ask farmers to dig a little deeper into what you're seeing?
I guess maybe questions because the existing literature or study mainly focused on what's the drivers of adoption. But I guess to my best knowledge, no study has asked what's the drivers of this adoption. I guess that would be very valuable and interesting question to look at.
Do you have an idea of how many farmers try cover crops one time and then don't ever try it again? Like they had a bad first taste and
because in this study we only asked in 3 years, I guess more as long as the research time frame is longer, we can get more insights because for these intermittent users, although we see some are adopters in the period 1 or 2, he disadopt, we cannot just call them disadopters because he might have to pick it up in 2021, 2025.
Any questions online? So how about we move on to our second presenter and then we can take questions for both at the very end.
Thank you.
Okay, so see if we can get there. Okay, if you want to share your screen, once I give you, there we go. Okay.
All right, so our second presenter is Dr. Kelsie Ferin. Dr. Ferin is a research scientist 1 at the University of Wisconsin-Madison in the Department of Plant and Agroecosystem Sciences. She received a PhD from Iowa State University and completed her PhD with research with Dr. Andy Van Lukey in the Department of Agronomy. She will be presenting on strategic integration of Miscanthus under future climate conditions.
Awesome. Thank you so much for that introduction. I'm very happy to be here virtually and presenting to you all today. And I will start my talk. So, possibly. Okay, so I just wanted to start with a quick overview of what I'll be talking about today. So I was asked to speak about my project that I had partaked in during my time as a PhD student as a part of the INRC funding, as well as how this funding has helped me throughout my professional development. And so for the INRC funded project side of things, I'm just going to give some brief background and motivation to orient us, as well as the modeling frameworks that we use, and then talk about some key results and takeaways. So one of the main goals of the work that I was doing with the INRC is to address water quality issues within the Raccoon River Basin, which is located here in central Iowa, in order to achieve nitrogen reduction goals. And so it's we should all be aware now that nitrogen loss within agricultural land production, especially in the Corn Belt region, it can be one of the leading causes for poor water quality, both at local water quality scales as well as downstream. And so in order to address nutrient reduction, one of the methods that we looked at was using the Iowa nutrient reduction strategy goal to reduce nitrogen loss by 41%. And within this goal, there's many tactics that you can utilize in order to achieve a reduction. Some of these being reducing the time or changing the timing and reducing the rate of nitrogen fertilizer application, introducing cover crops like our previous presenter just spoke about, and introducing perennial grasses onto the landscape. And so perennial grasses can be very key to achieving these goals because they are displacing these nitrogen intensive crops by removing them from the landscape. And so to show you a little bit of an idea of what I'm talking about with perennial grasses, I have a figure here that shows Miscanthus on the left, soybean and corn in the middle, and then switchgrass on the right. And my work that I'm going to be talking about today focuses specifically on Miscanthus. And so why is Miscanthus so amazing at reducing nutrient loss? Well, to start off, they can require less nitrogen application compared to typical row crops. And they also have a longer, more above and below ground biomass due to longer growing seasons, which can then reduce nitrogen loss. And this can happen especially during the shoulder season. So when a row crop is typically not within grown or planted on the landscape. And lastly, they have great economic potential. So they can be used for ethanol production, animal bedding, as well as building materials. So we want to know what my work has been focused in the context of future climate conditions. And so first we need to understand what could potentially happen with nitrogen loss under these future climate conditions. So we should be well aware now that the trends for future projections are showing warming temperatures as well as more variable extreme precipitation. And this can have two effects. One being a decline in crop productivity could be likely. And so when we have a decline in crop productivity, nutrient uptake by crops is then slowed, which can then result in potential increases in nitrogen loss. And additionally, under these changing weather conditions, we can also see increases in mineralization of nitrogen within the soil. And as a result, this can lead to even greater potential for nitrogen loss under future conditions than we are currently seeing today. So if we put this in the context of replacing these, poor quality or low production row crops on the landscape with bioenergy research crops, perennial grasses like Miscanthus, future studies have shown that Miscanthus production actually could be even greater under future climate conditions and thrive due to an even longer growing season, resulting in greater biomass. And the reason for this longer growing season being due to a delay in senescence or the dying down of the plant at the end of the season. And so by having these higher producing bioenergy grasses on the landscape for a longer period of time can then result in potential nitrogen loss reductions under the future context or climate context. And we know that it's not realistic to be replacing all cropland with perennial grasses on the landscape. So we need to be very strategic about how we're implementing this. And so an important thing to consider is thinking about the balance between food and economic security and the environment. And we do this with two methods, both considering economics. One is using economic modeling, which I also utilized throughout the other chapters of my dissertation while I was at Iowa State. And today I'll be focusing specifically on profitability analysis. And so this work that I have conducted is branching off of Brandis et al. 2016 and 2018, which are figures shown here on the screen, in which they calculated profitability at the field scale across the state of Iowa, and then use this in conjunction with areas of land that are likely to have high nitrogen loss and converting those specific regions to, in their case, it was switchgrass, but a bioenergy perennial grass. So throughout my time here at Iowa State, my research was mainly focused on agroecosystem and hydrology modeling. And the agroecosystem model that I utilized was Agroecosystem. And this is a process-based biophysical model, which simulates carbon, energy, water, and nutrient exchange between the soil, plant, and atmosphere. And a lot of these calculations are occurring at the leaf level at an hourly time step, so a very fine scale. And then it can also simulate crop productivity and growth, as well as, nitrogen loss at the daily scale. And we utilize this model to answer many questions. And another factor of this model is that these grid cells are independent of one another. So it's a gridded model. So we're able to simulate over a wide area of land at multiple spatial resolutions. For the work I did here that I'm presenting on today, it's at the 500-meter scale, so very close to a field scale as we can get. But in order for us to be able to simulate nutrient and water transport downstream, we have to utilize a hydrologic routing model. And in our case, we're using a model called THUM, which stands for the Terrestrial Hydrology Model with Biogeochemistry. And the biogeochemistry portion of that is coming from denitrification of nitrogen within the streams. And so we can utilize this model by overlaying a topography map in order to determine which direction grid cells should flow into one another to simulate downstream transport. And then we can look at nutrient loss as well as stream flow at the outlet of a specific basin. So for this case specifically, our basin was the Raccoon watershed here in central Iowa. And we used these two models and drove them with both historical and future climate data. We also needed to determine where specific crops were located across the landscape, and we did this in a simplistic manner by using cropland data layer and determined where continuous corn and corn soybean rotations are located, and then assumed the remaining land cover was just natural vegetation, which is a crop type or plant type that can be handled within Agroecosystem. And within the model, natural vegetation in urban area, nutrient loss is very similar to one another. And additionally, we worked with Lisa Schulte-Moore's groups, and specifically Ellen Audia, who was a master's student at the time, to calculate a field scale profitability analysis using Agroecosystem simulated yields. And this utilizes land rent price, input costs, and grain prices for each county. And we use this to economically determine land use change across the basin. And so this is following protocol from Brandis et al. 2018. And we used the thresholds of if profit within a grid cell was less than 100 or minus $100 US dollars per hectare, and the grid cell also lost more than 50 kilograms of nitrogen per hectare. And this nitrogen leaching rate is coming out of the Agroecosystem model for the baseline scenario. Then we would convert 100% of that grid cell from whatever crop type it was before to Miscanthus. And so you can kind of see this here with the little blue dots across the screen. Those are just the grid cells that were replaced with Miscanthus. So next I'm going to walk through some of my results. And I'll keep it pretty high level for the sake of time, but we looked at multiple scenarios that are laid out throughout this paper. And this scenario here is looking at the context of historical climate and current land use, or in integrating Miscanthus on the landscape. So if we had nitrogen leaching under current climate conditions, and we followed this protocol of finding the areas in which profit was low and nitrogen leaching is high, it results in a Miscanthus placement like so. And then we resimulate the model, and it's hard to tell visually just because the area of Miscanthus is pretty small. But in all, this reduced about 2% of row crop with Miscanthus, it replaced 2% of row crop with Miscanthus, and then resulted in about a 4% reduction in nitrogen loss under the current climate conditions. So switching gears and talking about nitrogen loss in the context of future climate, I had already prefaced on this, but we were expecting that nitrogen leaching under future climate would be increasing due to reductions in crop productivity, and then increases in nitrogen mineralization due to changing weather conditions, and therefore increasing loss. And that's exactly what we saw throughout the modeling simulations. And so today I'm only presenting on one of these future tracks, but we did consider both mid and late century and different RCP, or the representative concentration pathway warming scenarios as well. And so across the projections that we saw, about 64 to 109% increase in nitrogen loss was observed throughout the model under these future conditions, with no Miscanthus integration on the landscape. Okay, so if we're taking this future climate and now we're applying the same method of selecting low profitability, high nitrogen leaching grid cells of Miscanthus, we were getting maps similar to this in the middle. So a lot more blue grid cells appearing. So there's a lot more area of Miscanthus being placed. And this resulted in a visual reduction on the landscape just by comparing the first and last figures on the screen. And this resulted in about 15 to 17% of row crops being displaced by Miscanthus and resulting in a 19 to 26% reduction in nitrogen loss across the basin. So I'm just gonna end this portion of the talk with some key takeaways. And these key takeaways are from this paper, as well as the other work I did during my dissertation, as there's quite a bit of overlap. And so first off, strategically implemented perennial grasses do have the potential to reduce nitrogen loss and improve multi-scale water quality issues under both the context of current and future climate conditions. We found that Miscanthus can reduce nitrogen leaching and improve water quality. However, the environmental benefit of perennials is going to be much greater if it's placed on cropland, but the economic benefits of perennials are much greater if they are placed on idle cropland or marginal land or land that's likely to either fluctuate in and out of cropland or just doesn't have any crop or profitability in general. And then lastly, in order to ensure that water quality improvements across the basin are met, targeted incentives for nitrogen loss are going to be needed in order to displace these nitrogen intensive row crops with these perennial bioenergy grasses. So we're really going to need a big shift and a push to make this transformation happen on the landscape. And then I want to end this portion of the talk by my acknowledgements and giving shout outs to all the co-authors, as well as my PhD advisor, Andy Vanlucki. And if you want to learn more and go into more depth on the scenarios that I wasn't able to cover today, check out the paper. It's published in Global Change Biology, Bioenergy. Okay, next I'm going to be transitioning to the second portion of my talk, which is how has this funding helped me throughout my professional development. And so I'm going to talk about three main things. One, I was able to gain expertise in many things, but specifically from this work was being able to utilize agroecosystem and hydrologic routing models. And this has immensely helped me throughout my time, as it helped me get my position at UW that I have today. And I was also able to spend a lot of time creating and using spatial data sets that can tell us land cover, as well as simulating climate change, and being able to work these in with our workflow and answer many scientific questions surrounding them. Secondly, I was given the opportunity to collaborate across multiple groups on campus, as well as outside of the university, just because this project, as well as the work I did at Iowa State in full, was very interdisciplinary. And this allowed me to expand my knowledge. For one example is on economic analyses that I would not have been able to dabble with. I probably would not have been able to dabble with on my own if it wasn't for the amazing collaborations and the funding from this work. And the last thing I'll talk about, but certainly not least, is communication. And I was able to present this work at conferences and seminars, as well as improve my writing skills, as this resulted in a chapter in my dissertation and a publication. Additionally, this work has led to many opening new doors for me in new opportunities. And so what this resulted in was a postdoc position at the University of Wisconsin-Madison. I was offered this position as they were looking for someone who specifically focused on integrated modeling frameworks, specifically with Agroecosystem and the hydrology model, as well as economic modeling. And I had this experience from my time at Iowa State. And after 2 years of a postdoc, I transitioned into a scientist role, and I've been in this role for the last 2 years. I was brought on to this two projects here at UW, one being, they're both under the National Science Foundation Innovations of Nexus, or at the Nexus of Food, Energy, and Water Systems, which is no longer a program within the NSF, but the main work that I'm doing on this is twofold. One, I'm collaborating with a group at Purdue University and the University of New Hampshire in order to combine Agroecosystem with economic modeling and specific hydrology models, that can answer questions about how specific policy or taxation could improve water quality across the Mississippi River Basin. And then I'm also a part of this project called Fewscapes, which some in the room I know have been on a few of our stakeholder meeting calls. But what we do is we work with stakeholders, which include agricultural and natural resource professionals, policymakers, other scientists and educators and extension personnel that through this series of workshops, we've created 4 potential future landscapes in which we have the hopes of achieving goals surrounding food, energy, water, and ecosystem conservation. And my portion of this project has been to meet with our stakeholder groups and work with our team to develop scenarios and inputs to our modeling framework. And then I'm the person that is executing these models for multiple future climate tracks. And in addition to this work, I've also had the opportunity to be the modeling support personnel, as well as mentoring for the postdoc and PhD students that are here at UW specifically that use Agroecosystem. And so by having the many years and expertise of working on this since the beginning of my PhD, I believe this led me to having this opportunity that I do now. And lastly, I've been able to have many opportunities for further collaborations that I was able to gain at Iowa State as because of this project, as well as new collaborations moving forward. And so this work has really seeded my ideas and main focus on my research track that I had been going on, and this resulted in 4 co-PI pending USDA grants, and then hopefully, more papers to come within the future of that as well. So with that, I thank you. If you have, obviously time for questions, and if you want to follow up with me, my email's on the screen, and I'll give a shameless plug for our Fewscapes group. If you want to learn more, check out our website and subscribe to our mailing list. We are almost complete with our future simulations, and we are in the progress of updating our website to be able to house our simulation results, and also with the intentions of writing some reports to help either scientists create scenarios and further their research, as well as potential policy. So thank you very much. And I do have 2 extra slides I was told to add. I don't know if
I'll go over those.
you want to go with that? Okay.
So all of our seminars are recorded and they can be found on the INRC website under the videos tab, or by using this QR code. Then if you can go to the next. And our next seminar and our last for the spring seminar series, we have Eric Henning, who's going to be talking about recycling drainage water for irrigation, and then Esteban Gonzalez, who's going to be talking about the effects of winter cereal rye variety on corn growth and yield. Okay, so I want to give a round of applause.
I have a question for you on the modeling where you talked about the reduction with Miscanthus under the future climate conditions.
Yeah.
I can't remember what that percent reduction is or was, but was that compared to the future climate condition without Miscanthus? And I guess if you remember, if that was the case, how did it compare to kind of the current conditions, like current with cropland?
Yep.
So you increased because of the climate,
Yep.
And then decreased it with Miscanthus. Maybe how did it compare to what might be the current condition?
Yep, that's a great question. So technically, even with Miscanthus in the future, we are sitting slightly above where we would be under current conditions without any Miscanthus on the landscape. So, and that's laid out in the paper as well. We go through multiple comparisons between those. And so a little bit more would be needed to either get us at that baseline level that we initially started with pre-climate change, or just a different type of strategy incorporated within.
Thank you.
Yeah, thank you.
Hey, Kelsie, was your, when you were modeling Miscanthus, was that with the idea that it would be harvested and sold for biomass?
Can you repeat the last part of that question? You cut out a little bit.
I'm sorry, when you were thinking about Miscanthus on the marginal land, was that with the idea that it would be harvested for biomass and solar?
Yes. Yep, that was the main goal. This project was also co-funded through CABI. So that economic potential value was in consideration, even though we did not do any analysis on how much, ethanol production that might entail. And I don't have the numbers off the top of my head, but the paper does include biomass, total biomass harvested from the model for Miscanthus as well as corn and soybean.
Thank you.
Mm-hmm.
I might have missed it, but did you say how many acres were converted in your model with the changing climate?
Yeah, so under future climate, there was 15 to 17% of row crops converted to Miscanthus. Under the historical climate, that was only about a 2%. And so a lot more was just displaced under the context of future climate, because within the model, row crop yields had declined due to the high temperatures and weather variability just playing a role in that as well. We also, within the paper, which I didn't include in the results today, we did focus on optimizing the growing season length to allow this to be longer and then lengthen the time in which crops could grow and hopefully bypass some of the heat stress. And that actually resulted in greater corn yields, and that really drove the area of conversion down, as well as reducing nutrient loss as a factor. But that was just a small scenario, sensitivity scenario that we included in as well. So potential for that to be included in future work as we continue on with this stuff.
This might be a little too in the weeds, but under your future climate scenarios, did it predict more excess water stress?
That's a good question. Yeah, we didn't look specifically at that, but we did see reductions in yield. And that is a big factor of that. Like nitrogen wasn't being limited. So that nutrient stress wasn't being a factor of that. So I think with a combination of the water and just the heat, just warmer temperatures and, faster accumulation of growing degree days and reaching those phenology stages quicker. Within the paper, we also looked at stream flow too. And I believe the future years that were on the drier end or more variable in terms of the future climate, in terms of precipitation, did play a major role in us seeing reductions in crop yield as well. And that is laid out within the paper too, if you're interested in more about that.
Well, we still have about 5 minutes left, so maybe we'll open it up to questions for both of our presenters, if there are any. Well, I'm not seeing any online, so how about we just end a little bit early today, and thank you again to both of our presenters. Great job.
Thank you.
Thank you so much for joining us from Wisconsin.
Yes, it was a pleasure. It would have been nice to be in person, but it is a little bit of a drive.
It was nice to hear about this work. I know a little bit on what you're doing on the Fuse project, so it was great to hear about this. Thank you so much.
Yeah, thank you so much. And we look forward to seeing you hopefully in a couple of months at our next Fusescapes meeting.
Okay, all right.